Welcome back to Making Sense of NMEA 183 Messages, the second part. In part 1 we managed to cut the serial data coming from our GPS receiver into actual strings that make up a sentence. We also were able to classify several sentence types and identified everything that comes from our GPS receiver for now as a parametric sentence. We also parsed the address field of these sentences, and so we have now here our talker IDs and our sentence formatters. Card to the first part here, link in the description. So in the second part, I wanna actually decode these parametric sentences for the sentence formatters we encountered last time. Let's get started. And of course, we start with a wee bit of theory. Anyway, today we want to talk about these parametric sentences. And just as a short recap from part 1, they start with $, that's followed by a parametric address field, and then a comma-separated list of data fields, star, checksum, carriage return, new line. What data fields are actually contained in a parametric sentence is determined by the sentence formatter within the address field. These fields have, of course, specific types, and I'll refrain to go into another rant about the standard here. You'll see. We'll skip this section here for the moment. We will revisit that stuff later and have a look at information fields, specifically fields of variable length text of valid characters, which I will denote in the following as text. In the footnotes to some messages, you find the additional information that a text field cannot only contain valid characters, but also the reserved character tilde, so our escape character, or in the terminology of this standard, the code delimiter. And I write those as text, including tilde. But onwards now to the first approved sentence I want to decode. And that is for the sentence formatter TXT, a text transmission, which can either be just a short text or longer text in a multi-sentence message. And I'll be using syntax diagrams here again, just in a very compressed form. Believe me, these pages will get filled up as we go on. The first 3 fields have all the same formats, 2-digit. The first digit 0 to 9, the second digit 1 to 9. The first field gives you the total number of sentences in a multi-sentence message, 1 to 99. If there's only a single sentence in the message, it's of course 1. The second field gives you the sequential number of the sentence within the multi-sentence message. Again, if there's only one sentence in the message, it's always 1. The third field is a text identifier, 1 to 99, which describes the kind of text included in the message. Please note, that is not a unique ID for the multi-sentence message as a whole, as we have seen before in the encapsulation messages. This is in contradiction to the standard itself, where it states in 739 multi-sentence messages that these multi-sentence messages have to include such a message identifier. But anyway, they get away with that by calling it here for the text transmissions not a multi-sentence message, but a multi-sentence transmission. Sorry, ranting again. Anyway, fourth field is the text, or if it's really multi-sentence, the text fragment itself, with a maximum length of 61 characters, and that text might include the escape character. Now let's write some code. And here it is. I also added some commands here in the code so I won't get lost. So first we add some more types to our already long list of types, and for that I created here a macro which turns a 3 uppercase letter sentence formatter into a number, which will come in very handy. The macro works the following way. If you have a look at the uppercase letter A to Z in ASCII, you see that only the last 5 bits in their representation is changing. So if we logical AND that with a bit mask with only the last 5 bits set, we get something like that. 0, 0, 0, and then 5 bits of data. Now I take each of the letters in a sentence formatter and do that, but the first sentence formatter letter is shifted 10 bits to the left within a 16-bit integer. The second one is shifted 5 bits to the left, and the third one is not shifted at all. And if we all that up, we get that unsigned integer representation of our sentence formatter XYZ. So here the first letter, second letter, third letter. And we still have a bit left here for other purposes. Now on to the real types. Of course, I define another enum class for the parametrics fields type, which is of course an unsigned integer this time, and the first value in this type is the TXT for our text transmissions, which is a numerical representation of the sentence formatter TXT derived by the macro. And that's the reason I'm using a macro here. You cannot really initialize the values inside an enum with a function. It would have to have be a constant function, and yeah, that's not really doable. So I'm using a macro here. And the second value for now is of course unknown, all 16 bits set to 1. And don't worry, I won't do a complete code walkthrough for each and every sentence we've encountered so far. Maybe I do 1 or 2 more after text, yeah, every time I employ a new technique for decoding them. Then we have the struct NMEA parametric fields text, which holds, of course, the data of our text transmission. So the total number of sentences in that multi-sentence transmission, the sequential number of this sentence within the transmission, the text ID and the text message itself, 62 characters. The standard defines 61 characters as maximum length, but I will handle that as a real C string, and so I'll add a \0, so a 0 byte at the end of the string. Finally, we have a struct NMEA parametric fields, which contains our parametric fields type, and in a union, I talked about that union stuff already in part 1, we find our struct NMEA parametric fields text as text. And that is added to our NMEA data content here in a union again, which contains the parametric fields as parametric, and later on maybe also encapsulated fields, query fields, and proprietary data. Much further down, I added something in our NMEA decode function, and to be exact, inside the case statement where we actually decode the parametric messages, I added here content parametric will be equal to a new function NMEA decode parametric fields. And that function gets as an argument the content address approved formatter, our 3-letter formatter, then the sentence characters, but not all of them. We start at the 7th character, so after the comma, after the address, and the sentence length is reduced, of course, accordingly. So the 7 characters we skip at the beginning, and the 5 characters that come at the end, so the star, checksum, carriage return, new line. To implement that NMEA decode parametric fields function, I've defined 2 helper functions. The first one here, NMEA sentence formatter number, is just encapsulating the macro. So that turns our 3-letter sentence formatter into an unsigned integer. I just don't like to use macros all the time in my code. Then we have the NMEA chop parametric fields function. That turns our character array into a lot of strings within that string. You'll see. So I have a variable I here, and I also keep a count of the fields within our character array, which is initially 1. Then I go through all the characters within our character array, and if it's not a comma, I simply copy the character over into our string. But if it is a comma, I increase the field count. Yeah, we encountered a comma, so another field. And instead of the comma, I copy over a \0, so a nil byte. And at the very end, I append at the end another nil byte, yeah, completely terminating that string, and then I return the field count. Now we can have a look at the NMEA decode parametric fields function itself. We already know what parameters are passed to it. So I have a buffer variable here, fields, which will hold the data of our parametric fields. I have here a string variable that will hold the string within string, the chopped up fields, and a field count. And I'm using the NMEA chop parametric fields function to chop up our character array of a certain length into that string of strings. I also get the field count back. Then I switch according to the number of the 3-letter sentence formatter in that case statement. And if it is indeed the number for text, I assign the field's type as text, and I assign to field's text the data, the result of NMEA decode parametrics fields text, which I pass the string and the field count to. Otherwise, a field's type will be unknown. And at the end, I return my field's data. After all that preparation, the NMEA decode parametrics fields text function is trivial. Of course, I have here a buffer here for my NMEA parametrics fields struct, and then the first member of that struct is simply the first field, yeah, 0 terminated string, converted into an integer. Then I move on to my next field simply by taking the length of the string and skipping the \0, and I do the same for the sentence number. Moving on to the next field and getting the text ID. Moving on to the next field and then simply copying that leftover string into my text message. And then I return the whole shebang. Of course, I also extended the NMEA print data content function. That function now contains at the very end another switch statement according to the data type, and if the data type is indeed parametric, I call the NMEA print parametric fields function. And that function, of course, contains another switch statement according to the field's type, and if the field's type is text, I call the NMEA parametric fields text function. Otherwise, I just print out unknown. And the NMEA print parametric fields text function just prints out our struct here in a nicely formatted manner. Now, let's have a look how that looks on the serial monitor. We've encountered these text messages when we started up the device, so let's cut the power to it and disable auto scroll and clear everything here, and let's start up the device again. Here. Okay, that was our first sentence somewhere about the hardware of our GPS module, and it's now nicely decoded. So from the talker GN we get a text message. That's part 1 of 1, and the ID of the text is 2, and it's obviously the hardware ID of our module. And then the second string here is also decoded, same, and the ROM core is 2.01 from 2013. So that GPS module from uBlocks is really old stock. That's probably why it was so cheap. And the protocol version is 15.00. That's also very old. So yeah, and the rest is also decoded quite nicely. Let's do one more today. And this time we will actually decode some position data, I promise. But before we have a look at the sentence, we need to revisit the data fields. The standard states if the value of a field is not available or reliable, then the field should contain no characters, so it will be just comma, comma. The standard calls that a null field. Of course, that applies especially to our GPS receiver. If the receiver doesn't get any GPS signals, its position information is not available or not reliable, so the related fields should be null fields. That brings us to the special format data field types latitude and longitude, which are quite similar. So the format for latitude is degrees, degrees, minutes, minutes, and then after a decimal point, fraction of a minute. This field is of course nullable if it's not available, but the regular expression for it, if it's there, is 4 digits followed optionally by a decimal point and then 1 or more digits after that. And I will denote that by latitude and optionally comma nullable. Longitude is almost the same. The only difference is you have here for degrees an additional digit, and that will be longitude, optionally nullable. Then we have the data type time in the format hour, minutes, minutes, seconds, seconds, optionally after a decimal point, fractions of a second. It's also nullable, so it usually starts with 6 digits and then optionally after the decimal point, 1 or more digits, and I'll write that as time, optionally null. With these additional data types under our belt, we can have a look at the parametric sentence GLL, Geographic Position, which gives us the latitude and longitude. It starts with a nullable latitude field followed by an optional letter N or S indicating if the latitude is north or south. Then comes a nullable longitude field followed by an optional letter E or W, which indicates if the longitude is east or west. Then we have a time field, also nullable, which gives us the universal time coordinate at which that position was taken. And then we have a status field that is not nullable, and it's the letter A or V. A stands for valid and V for invalid. Don't ask me why. The last field, so a single letter in that case, represents something new syntax-wise. So instead of having a comma and nothing here when the field is not given, we completely skip the field, including the comma and the message. The reason being that field was not present in that sentence in NMEA standards before version 2.3. If you have watched my video about NMEA standards in general, you'll know that NMEA 0183 is all about backward compatibility to older versions. Card to the video here, link in the description. So, in 7.3.11 additions to approved sentences, the standard states that existing sentences can be extended in future versions by adding fields at the end of the sentence, and that's what happened here. But now for the field itself. So it's a single letter ADEMNS, and it indicates the mode your position system, so your GPS receiver, is running in. For a status of valid, it can take the values A for autonomous or D for differential. You heard probably about differential GPS. For an invalid status, it can take on the values E for estimated, so just an estimated position, M for manual, so somebody typed in that position somewhere, N for no fix, so we have no position, and S for simulator, so just simulated data. Now let's write some code. And here it is. Of course, we start with some new types, or not with new types, but what I did was, of course, uncomment here in my parametric field types the GLL line. And then we have a new struct here, NMEA parametric fields position. And that struct will contain all our 4 position fields. And yes, I just edited that in. So the latitude north-south, then our longitude east-west. And it will have a flag if it's nullable. Well, not if they are nullable, but if they have been in fact nulled in a sentence. So I'm breaking up my latitude here into 3 fields. I'm doing that because the float of the Arduino has only 6-7 digits precision, and that's not enough. So I have here a byte for my degrees 0 to 90, a byte for my minutes 0 to 59, and then a float for seconds and fractions of a second. That's just the fractions of the minutes we have in our sentence times 6. And of course I have here a char to hold the north-south indicator. I'm doing the same for the longitude, the only 2 differences being that longitude degree is from 0 to 180 degree, and the char here is of course east-west. We will see this combination of 4 fields to indicate a position quite often in NMEA sentences, so it's a good idea to give it its own type. And next we have another complex type, the NMEA parametric fields time. Same principle, just applied to a single field. So we have here a boolean if it's nulled, and I store my hours 0 to 23 in a byte, by minute in a byte 0 to 59, and a float seconds, so seconds and fractions of a second. And with that we can actually define our struct NMEA parametric fields GLL, so finally our geographic position, which consists of course of our position, our time, and then our status char, so A valid, V invalid, and our mode char. I didn't list every mode here, but if that field is missing, you remember it's only available in newer versions of the protocol, then I set it to a nil byte. And that struct is added to our union within our struct NMEA parametric fields. And that's it for the types. Much further down in our function NMEA decode parametric fields, I add analog to the case statement we had for the text sentences, a case for our GLL sentences. And I also have a new function here, NMEA decode parametric fields GLL, which returns the content of the GLL member of our union. Then I have 2 general helper functions here for decoding fields position and the time. And the first one is the NMEA decode parametric fields position, of course, which returns a position struct. And it gets basically the same parameters as all the other decode functions, so the string and the fields. But please note, I'm passing that string here as a reference to a char pointer. Though this time, if I change something in the function at that string pointer, that will be visible to the calling function. I have, of course, a buffer variable here, position, and then here a pointer to an actual field I'm decoding and a pointer to decimals, which we will use. And I assume in the beginning that the fields are not null fields. Then I start decoding my first field, that's the latitudes and degrees and minutes and fractions of minutes. To do that, I first save a pointer to exactly that field, and then I jump with my string pointer already to the next field. So if the length of the field is greater than 4 characters, then it's obviously a valid field and not a null field. And I start decoding it backwards. So I search first for the decimal point, and if I find the decimal point, then from that position on I convert everything into a float, multiply it by 6, and that gives my latitude seconds. Then I write a nil character at that point, cutting the end of the field off. Next, I decode my latitude minutes, and that's simply the start of the field plus 2. And then after 2 characters, there is our \0. And that's converted to the integer. That is the byte. Then I write a 0 exactly at the start of that field. And I decode the rest as integer and write it to my latitude degrees. If my field was too short or a null field, then I write position null equals true. The next field, north-south, is more or less trivial, so I simply assign the char here latitude north-south, our string 0. Remember, we already advanced that string pointer to the next field. And if it's a \0, so end of field, then also my position null is true. I have a null field in my position, then the whole position is basically invalid. And I move on to the next field, which is longitude, degrees, minutes, also here fractions of minutes, and that works exactly the same as the latitude, so nothing new here. And at the very end, I advance my field once more and I return my position. Please note again that these advances in the position in my string of strings has been passed up to the calling function. Okay, second helper function, a little bit more easy on the eye, is my NMEA decode parametric fields time. That function follows the same principle. So the string is passed as a reference to a char pointer. I have my buffer here for time. I have a pointer here, helper pointer for fields. And I have a pointer for decimals because our field can contain fractions of a second. And yeah, I assume in the beginning that it's not a null field. So I save my pointer to the field and I advance to the next field, my string pointer. And if the field length is greater or equal 6, then it's not a null field. Otherwise, of course, it is a null field and I set null to true. And I also decode that thing backwards. So first I go to the second position and convert that into a float and assign it to seconds. Then I write a \0 at the start of the second field or the second portion of the field. Then I decode my minutes integer into minutes. And then I wrote a \0 at the start of the minute portion. And then finally I decode the hours. And at the very end, I return the time. So finally, we can have a look at the NMEA decode parametric fields GLL function. Yeah, absolutely nothing new here. The function itself is almost trivial because I'm using that toHelper function to decode my first 5 fields. So 4 fields for the position and 1 field for the time. Status is simply a string copy then from the actual fields, and then comes something new. I finally use that field number here. So if I have more than 6 fields, then obviously my GLL mode is coming. So I advance my string pointer once more and I copy that character into my mode. If that's not the case, if I have less than 6 or less fields, then I write \0 into my mode, a nil byte, and I return the whole shebang. Of course, I also extended the print functions. So first in NMEA print parametric fields, I added the appropriate case here for GLL, and I'm calling the new NMEA print parametric fields GLL function. And then I have here two helper functions for position and time, because we will reuse that properly. So NMEA print parametric fields position, and I'm not going through all the hoops here and explain how to print and format something on an Arduino. It's quite a mess. For example, the sprintf function doesn't support %f. You have to use the d2string_f function to convert a float into a string, and that doesn't support leading zeros. So yeah, quite messy. But I either print my position nicely formatted, or I print here null position. The same holds true for the print parametric fields time. I go through all the hoops here to format it nicely, and if it's a null field, I print null time. And then finally, we have the NMEA print parametric fields GLL, which prints the position, the time, then our status as valid or invalid, and our mode either as mode or nothing, because yeah, it's not available in every version of the protocol. Now let's have a look at the result. And yeah, it seems to decode these messages just fine. So here we have a GNGLL. We already decoded the address part, and now it says it's a null position, null time, it's invalid, and it's mode N for no fix. But let's position the receiver somewhere near a window so we actually get a fix and a position. And through the magic of an USB extension cable, I was able to place the receiver up there on a stand and keep my notebook on the desk. Unlike in the mailback video of that thing, card here, if I haven't carded it, link in the description, where I was standing with the notebook at the open window at freezing temperatures. The window is closed. I still get some reception, not a good reception, but it gets a GPS signal indicated by that 1 second blink here of the green LED. Okay, let's have a look at the position now. And there it is. Let me see. Okay, down here we have a GNGLL, and yeah, GNGLL, and now we have here our position. So 48 degrees, 45 minutes, 5 seconds, something north, and 9 degrees, 9 minutes, 4 seconds, something east. And no, there's no privacy issue. The reception through that double pane isolation window is so bad. These coordinates are quite off, okay? We also get our time here, so it's 1733 UTC. 11 seconds, yeah, no decimals at the seconds, and we have a valid signal now, a valid position, and mode A for autonomous. Great! Next time we will tackle a sentence that has a variable number of fields. I'm not talking about additional fields at the end of the sentence that came with newer versions of the standard, but really a sentence of variable length. And after that, it's smooth sailing, and I won't go into the details of the code for other sentences anymore. Promise. Till then, bye.